Hello everybody and welcome to our video today, which is going to be relatively short because a lot of the things in this chapter have been covered in previous chapters. But we are talking about Organic Chemistry, Chapter 9, the derivatives of carboxylic acids. So, just as a refresher, we have carboxylic acid, right, which has a hydroxyl group and a carbonyl carbon. Then we have an ether, which is an R group attached to an oxygen attached to another R group. Then we have an ester, which is an R group attached to a carbonyl carbon attached to an oxygen with an R group, okay? And then we have amides, which are formed by the condensation of a carboxylic acid derivative with an amine or ammonia, right, to get this N, which is part of our amide here. So one important reaction in this chapter is called esterification, and this is where we take an alcohol plus an acid and we form an ester. So we start with this primary alcohol, okay, and also we see here that this oxygen is going to be positively charged because it has 3 bonds, right? So this bond is going to break, and this is going to be attracted to this partially positive carbon here, and so we're going to attach our this alcohol, and we're going to get this kind of structure here. So now our oxygen only has 2 bonds, but we have this oxygen down here that now has 3 bonds, which now has a positive charge. So then what's going to happen is in order to satisfy this charge and recreate the bond up here, we're going to have this OH group, okay? This hydrogen is going to come to this OH group, which is going to create water, right? H2O is a good leaving group. So this, I'm going to make sure you can see, yes. So the water is going to leave, and then that's going to allow this bond to reform down here. And this is the structure we're going to have. But again, we have a positive oxygen because it has 3 bonds, and we're going to get rid of this hydrogen, and then we're going to be left with our ester. So that is the basics of esterification. Just trying to see if there was anything else I missed here. I think we covered it. Oh, the cyclic esters are known as lactones. I know that's something that I didn't necessarily know at the beginning, but I just wanted to share that. Cyclic esters are known as lactones. So next, we're just going to talk about some reactivity principles. And those are, important for all the reactions, but just a little recap for this chapter. So we have steric hindrance, which will play a role in reactivity. So if you're trying to react with this OH compared to, this OH, for example, you have all of this space to attack, right? You can't come over here because there's a bond there, but you have all this space to come at this OH group and attack it, right? If we're looking at this, our space that we can attack gets a little bit smaller, right? That's not as, you can't come from here, you can't come there, you can't come there, you can't come there, you can't. So this area is all we have to work with. So that's basically the idea of steric hindrance, is that the more the more substituents involved around where you're trying to react will make it more difficult to react at that place. Then we have induction, which is the distribution of charge across a sigma bond. And this is affected by electronegativity. So we see that a lot, with the carbonyl carbons and oxygen being a very electronegative atom. And then we have conjugation, which refers to our little cyclic ring here. And all of these carbons here will have a free p orbital because they are sp or sp2 hybridized, right? So which means they have a free p orbital, which means that space, that orbital, is able to delocalize the electrons and kind of accommodate for those electrons and becomes more stable. So that's why this conjugation of this ring is really important. Yeah, so that was kind of the basics of this chapter. Like I said, pretty short and sweet, just covering a couple of things we haven't covered already. If you have any questions, please put them below. And if not, we'll see you in the next video.